Okay, I hope you're all doing well. I got to cycle in without being rained on. That makes it a good day so far. Let me turn it over to other Brian with the power to write stuff that you can see. And I've got my Slack channel open. Okay, so let's make a start. We're looking at using a Fourier series representation to analyze, and this works for any constant coefficient linear Cauchy problem. Remember, a Cauchy problem is an initial value problem for all space. We're only talking about one-dimensional space, but this generalizes to higher dimensional space. People are asking, did I get enough coffee today? No, I didn't. I got tea. I only had 1 cup of coffee at home. It's sad start to an otherwise promising day. So what did we do last time? We did the heat equation. Well, let's try out this game on the wave equation. Whoop. So we want to look at UTT is UXX for all x with initial data. And I need initial data for the time derivative as well. Okay, so that's this is the Cauchy problem. So, well, we're going to write U in terms of its Fourier series. Here are the Fourier coefficients. Oh, in my notes, these Fourier coefficients are time dependent, and I didn't get that in the notes. And so this is a technique where really we're looking at the function of x at a given time, so some function of x, and we're converting it into its frequency components. That's what these things are. And I could have used omega instead of alpha, but omega makes me think, oh, d alpha, thank you, d alpha. Is that right in the notes? Okay, it's right in the notes. Okay, good. Thank you. I could have used omega, right? That's a typical thing people will use for an angular frequency. But this is really the Fourier transform in space. And so you talk about wave number instead of angular frequency. It's the same story. Okay, so, and then what we would do is take this form and we would plug it in. And we'd see that the Fourier coefficients all match up. And we end up with the following differential equation. So I get the time derivative of these guys. And when I take the space derivatives, I get minus alpha squared. That's every time you take a derivative, you multiply the transform by I alpha. So if I take 2 space derivatives, that gets me minus alpha squared. This is a pretty easy problem to solve, constant coefficient. I don't actually have to write down the characteristic equation, right? That quadratic, I can just look at this and go, hey, those are sines and cosines. And if this was plus alpha squared, which we'll see later on, then we'd have e to the absolute value of alpha t, and then e to the minus absolute value of alpha t. But here, it's pretty clear. I'm going to have some coefficients, which will depend on alpha times cosine alpha t, plus some coefficients sine alpha t. And this is all for alpha not equal to 0. When alpha is equal to 0, I just get d2 u hat dt squared is 0. That gives me the a of alpha plus b of, or a of, hang on. I'll put a 0 t. Okay, so another correction in the notes. This is for alpha equals 0. Okay, and of course, what we know should come out of this is D'Alembert's formula. So if I wrote this in complex notation, so I had, c e to the I alpha t plus d e to the minus I alpha t. And if c and d are complex conjugates of each other, then you end up with this form, and there's a relationship between the real and imaginary parts of c to a and b, right? So it's an equivalent form. If I look at that and I work out what the solution would be, right, with those coefficients, right, and I did some work, I would get D'Alembert's formula. So it's a different way to get what we had before. Okay, but this seems pretty good. Let's try another one. Let's look at the Laplace problem. As a Cauchy problem. So normally we would write it as uxx plus uyy is equal to 0. But if I'm going to write it as a Cauchy problem, I'm just going to pretend that one of those variables is time. And I'll give initial conditions, same as before. Now, I've told you that the Cauchy problem only makes sense as a boundary value problem. So something funny should come out of the analysis that we're going to do, or I'd be lying to you this whole time. Now, you know that I'm mistaken sometimes, and I make a lot of typos, but I don't lie, actually, unless it's to protect someone. So you'll see what happens here. You'll see, in fact, that the Cauchy problem for the Laplace equation doesn't make sense. Okay, it's going to be ill-posed. And then later on this lecture, we'll look at Laplace problem in this semi-infinite setting, formulated with the right kind of conditions, and show that is a well-posed problem, and we'll even find the Green's function for it. Okay, so you're expecting, based on previous conversations, that something bad will happen here. Anyway, so we'll do the same thing. We'll look at the Fourier transform, and we'll get d2u dt squared. Right? Now it's going to be minus alpha squared u hat, just the sign change. But remember, I warned you about the sign change that will lead to exponential behavior. The alpha equals 0 solution is the same, but that's not interesting, right? And here we look at this term, right? And we'll see, right? There's alpha can be as big as you want, right? So this is unbounded. exponential growth. So this problem is ill-posed. Now, I know from past experience, students have a little trouble sometimes wrapping their head around this concept of being ill-posed. And so let's have another pass at it, just in case that helps you sort things out. Remember, real problems coming from applications can have exponential growth in them, right? If you are studying some mathematical problem with investment income, right? Well, in fact, you hope, right, your investments will grow, right, over time exponentially, right? Exponential growth is fine. Of course, if you don't want something to grow, right, exponentially, then it's interesting if you do the analysis on your model and you find that it does. But that's not a killer of the model. Exponential growth is fine, right? And you can have large exponential growth if you are looking at the dynamics of an explosion. You could imagine that very small changes in the initialization of the explosion can lead to, drastic differences in behavior later on, right? So exponential growth is okay, and large scale exponential growth in data is also something that can happen. What's not okay is this unbounded exponential growth. Because what this is saying is you can make an arbitrarily large change in the solution with an arbitrarily small change in the initial conditions or the data, right? And that's not a well-posed problem. That's not a problem that you can say, okay, I have the solution and I trust, this solution will behave something like this in real life, because you can't control infinitesimal changes in the data that you give a real system. So okay, when I say the Laplace problem really only makes sense as a boundary value problem, not as an initial value problem. Here is the evidence in this red box, right? That's if you try and formulate the wrong kind of problem with the wrong kind of data, your problem doesn't make sense anymore, right? Ill-posed. Maybe I'll pause here and give a chance for students to ask any questions they have about this idea of being well-posed or ill-posed. I'm happy to go through another pass if it's needed.
Yeah, I've got a question. So to summarize what an ill-posed problem is, could we just say it's just really difficult to solve, or doesn't make any physical sense?
No, it's not. A really difficult problem to solve is ill-conditioned, okay? That's when the result depends strongly on some, very sensitively on some conditions you have to give it. That's a poorly conditioned problem, ill-conditioned problem. Ill-posed is worse than that. It's not a problem that makes sense, right? There's lots of problems that are hard, but ill-posed is not hard. It's a problem that doesn't make sense to ask.
Oh, okay. I think I understand it.
Okay. Any other comments on this? This is an important concept.
So is the definition of, I guess, ill-posed simply that an arbitrarily small change can cause an arbitrary large change in solution?
Yes.
Does that encompass?
Yeah.
I think I'm a little confused then about how ill-conditioned is different. Because you also said that, is it just a high sensitivity? That sounds a bit arbitrary and like it could be addressed with scaling.
Well, so when you talk about a problem being ill-conditioned, yes, it's arbitrary, right? How hard does it have to get to be hard, right? I mean, it's like Math 400 assignment questions, right? So some of them are hard, like which ones, cross the line to being really hard or impossibly hard, right? It's that's a line, that comes. So if I can use an analogy to computational problems, because I'm a computational guy at heart, right? All the work that we're doing in Math 400 is work I do that leads up to the model that then I have fun, figuring out how to compute approximations for. So there, back in the old days, floating point representation used to be single precision, so 6 digits, right? And people would talk about an ill-posed problem being one where your loss of accuracy during the computation was so big that you had very few significant digits of accuracy left in the solution. So that would be sort of a way to define ill-conditioned, but it's based on like the resolution that you have, right? So now everything is double precision, and so problems that are ill-conditioned are worse than they used to be back, decades ago. Maybe if I can pretend to understand how experiments work, because I'm a mathematician, because I'm not good at experiments, right? You can have an experiment that's very sensitive, right? You've got a knob that you're turning, and you only turn it a little bit before some drastic change happens that you want to measure. How sensitive does that have to be before you say it's sensitive? Okay, there is some arbitrariness to that. It's basically, if you think, how hard is it to get the resolution on the quantity that you want to understand, right? If it's really hard, you talk about it being ill-conditioned. And if it's sort of a straightforward computation or experiment, then you say it's well-conditioned, easy. I know that's vague, but it's because it's a vague line.
No, that kind of makes sense. So ill-posed is a mathematical fact, and ill-conditioned is kind of a function of the tools and the abilities you have to solve it.
Yeah, it's a hand-wavy thing, but ill-posed is not, right? Ill-posed is the red flag.
That makes sense, I think. Thanks.
Okay. The red flag, the black dot, whatever signal of doom that you have.
I don't think you have notifications on for Slack, Brian.
No, I'm seeing it's coming up. There was a little bit of a delay. So what's bad here is the high frequency component. Yeah. So the thing that's growing exponentially fast here are the large alphas. That's the large wave numbers, I would say, rather than frequency. But yeah, same thing. So these are tiny little wiggles, right, that you can add to the initial conditions, right, that lead to huge changes in the solution. Now, it doesn't always have to be high wave number components that lead to the ill conditioning, but it often is. Okay, so yeah, it's exactly that. You can have tiny wiggles that are high frequency, right, leading to huge changes in the solution. But the key to actually saying this mathematical thing is not that there is exponential growth or large exponential growth, it's that it's unbounded. Okay, so that's a key. If you have bounded exponential growth, well, okay, you got a system that has exponential growth in it. Right, and of course, I talked about money, but you could have bacteria growing exponentially in some initial time period, and so on. Right, those are all things that models are supposed to predict. Okay, let's do another one. Okay, here's another ill-posed one coming up. This was the one posed by a student. I'm not good with names, so I regret I don't remember who said this. We were talking about different equations, and they said, "What about this equation?" Right. Okay. So let's look at the Cauchy problem for that one. Right. So that would, once we do this Fourier series thing, derivatives in x are just a multiplication by I alpha. Right. And so now you see I've got to work out the square root of I alpha. All right, so now I'm in the complex plane. I've got this thing I alpha. I have to figure out the square root of it. Okay, now you have to think back to what, Math400, right? 305 something, I can't remember like what course you would have had. But right, this is a 90 degrees, so the square root goes out at 45 degrees. So here's one of the roots. This is 1 plus I over the square root of 2 times the square root of alpha. Right, and then of course you got the negative one. This one is minus R of alpha. This is minus 1 plus I over root 2 root alpha. Okay, I have no idea where this kind of equation could come from, but it's ill-posed. So we'll see that in a second, right? Because now I've got my two roots of the characteristic equation. Okay, and in all my prepared notes, I forgot the t dependence to put in here, right? So this is going to be, well, one of them times e to the r alpha. This is the one that's going to be ill-posed, so I'll just leave out the other one. I've got e to the t root alpha over 2. That's this real part. And then I've got, I'll just put it as a complex exponential. Okay, so there you go. You got that behavior, and now you can see. Okay, it doesn't grow as fast. The exponential growth doesn't grow as fast in alpha, but it's still unbounded. This is unbounded exponential growth. So this problem is ill-posed. Well, okay. There's all kinds of ways you can go wrong when you're modeling new phenomenon. And you may have come up with this equation thinking, oh, this is a reasonable model of some behavior that you're interested in. Okay, and so, and of course, there could be all kinds of coefficients, nonlinear coefficients right in front, right? But if you forgot those coefficients, except their signs, and did this kind of analysis, you would see that there was something wrong with the model that you had put together. If you try and compute this, right? So if you do a sort of straightforward computation based on this, finite difference or finite element analysis, what you would find is you would have all these kind of wiggles would come into your solution that were large, and how those high frequency components behaved would depend on the numerical parameters of your solution, right? In a way where, as you refined your mesh and your time step, you would see things getting larger and larger, blowing up. So that's the sort of numerical outcome of ill-posed problems. Okay, another question's come in. Are there other classic signatures of an ill-posed problem beyond unbounded exponential growth? No, I think that is the signature, at least for linear problems. Okay, now that's a good question. Let me think. In Math400, no. Okay, other ill-posed problems out there? I mean, you could think of, but it's not ill-posed, right? You could give the wrong kind of conditions, so you overdetermine a problem and you don't have a solution. That's not really ill-posed. So no, I'm going to go with certainly, at least for Math400, this is the route to ill-posedness. Okay, I got one last one we can do in this Cauchy framework, constant coefficient. I'm going to talk about the Telegrapher's equation. And as a little caveat, I'm going to say it's got coefficients that are chosen so that something easier than the generic case happens. Okay, so actually I Googled the Telegrapher's equation, and there's some nice notes made by my retired colleague, Joel Feldman. You might want to have a look at that, about where this equation comes from, and there's a discussion at the end where he has some of this type of analysis, where you can see how these easy coefficients, where I just picked an example, but where these easy coefficients come from a tuning of physical parameters. Okay. So what have I got? I've got the wrong sign already. This is the wave equation with speed 1 with some lower order terms. Right, so if we were going to characterize this problem, right, the character of the problem only comes from the highest order terms, unless one of them is 0, right? One component of the higher order terms is 0, in which case we have the heat equation. We have to look at the lower order terms then, but not in this case. This is a hyperbolic equation, right? And when I do the Fourier series, this is a time derivative. This is the diagonalized thing. This is still a time derivative, and this is just a coefficient. So I've got the d2u hat dt squared plus 2 du hat dt plus alpha squared plus 1 u hat is equal to 0. Okay, and so, hey, this is a second order constant coefficient ODE, like all the other ones have been. This is not one we can just write down the solutions for. Okay, we gotta make the trial of e to the RT, leading to the characteristic equation. And then I look at my quadratic formula. I memorize a slightly different quadratic formula than most people, but here it is. And you notice that the ones cancel out, and I get, oh, sorry, -1 plus or minus I alpha. Okay, and so my solution then, there's a e to the minus t, right? So I have some exponential decay, I'll call it damping, that's independent of alpha times the same kind of wave equation behavior we had before, which I could write in complex form. This is alpha not equal to 0. You get that special case for alpha equals 0, same as before. Okay, so this is the wave equation behavior. And the telegrapher's equation is really well, it's actually from when people used to send telegraph signals down wires. This is a model of the loss in those signals as they propagate down the wire, right? So they will decay exponentially. The interesting thing here with the well-chosen coefficients, well, they're well-chosen, I mean, this analysis was particularly simple. The well-chosen coefficients, and you can see this in Joel Feldman's notes if you're interested, it's tuned so that the wave equation speeds, Matt, thank you. Or Matthew, I don't know if you go by Matt or Matthew, has just posted the link in the chat. Thank you.
I was just trying to figure out what the telegrapher's equation was.
Yeah, so you can see that there's a tuning so that the wave speeds don't depend on the wave number, right? You can see these are all going to be waves traveling with speed 1 if you look at them in the complex exponential form. Whereas for other coefficients, you can get distortion in the signal where different different wave number components will travel at different speeds. Okay, so that's the end of our Fourier transforms identify the behavior in all constant coefficient linear Cauchy problems. Let's go back to the Laplace problem. Okay, so we saw that the Laplace problem as a Cauchy problem was ill-posed. Okay, and you know, how much intuition do you have? But at least I've told you the Laplace problem only makes sense as a boundary value problem. So let's consider it as a boundary value problem. In half space. Right, so I'm going to have Laplacian of u is equal to 0 for y positive. I'm going to have all of x. And now I know it doesn't make sense to give u and uy here, right? And expect to get a reasonable solution. It's ill-posed. But I should be able to give boundary values here and get a solution. Well, except, right, there's a kind of a boundary, if you want to think about it, right? As I go out to y is equal to infinity, right? I could, you know, have a wall up here, right, at large y. And it turns out, I don't know, I think I've called this a hidden boundary condition in the notes. We've seen things like this before, sort of like this anyway. Remember when we were talking about solutions to the Bessel functions, right? We for the modes in the unit disk, we needed an extra boundary condition at r equals 0, and we didn't have a value or a derivative or anything concrete. It was just that the solution was bounded there, because one of the homogeneous solutions was unbounded there. So by saying it's bounded, you're automatically picking the other one, right? So let's just say that this is a hidden condition or an extra condition that the solution will be bounded as y goes to infinity. And this is acts as a boundary condition. Okay, so let's do that. Well, we did the algebra already, right? I'm just using y instead of t, right? We had a solution which showed that it was ill-posed. Here, let me clean that up. Oh, sorry, I haven't got there yet. Right, okay, and then I've got the A0 plus B0 times, well, let me do it this way, because then it'll make it work out. This is for alpha not 0 and alpha equals 0. Okay, and so the boundedness means that these have to be 0, right? So that means I just have to look at these coefficients at y equals 0, and I get that b of alpha has got to be, well, it's just the transform of the boundary value data, right? Because this is got value 1 when y equals 0, and this does also, right? So now I've got my solution. U hat of alpha is u hat of the initial conditions e to the minus alpha y. Okay, so well-posed. We can go a little bit farther, right? With the sort of tricky things that you do in a typical Math400 course, okay? Or you might have seen it sometime in an earlier course, I don't know. So the transform, right, of the solution, and I keep forgetting to put the time dependence. That's missing in the prepared notes, right? The transform of the solution is at every time, right? Is given as a product of Fourier series. And so using the properties, yes, thank you, Julie. Right, that's why. I had the T from before that I kept forgetting, so that's why I automatically put it in, but yeah, we're in Y now. So at every Y, right, this is the transform is the product of two transforms, so that means u of x and y, so this is u as a function of x at a given y, is a convolution at every y with the initial data and a function g. And the only thing we know about g so far is that its transform is e to the minus alpha y, with alpha with an absolute value. Okay, so you can have that function, right? And basically you look at the e to the minus y and you handle alpha with some a scaling argument. So you can look in tables or Wolfram alpha or you can do contour integration. And you can find that this g of x, and I've put a slightly different notation, right? This is g is a function of x with y as a parameter, basically, right? This is 2y over x squared plus y squared. And so remember, if you go back to the notes last time, the convolution has got this factor of 1 over 2 pi in it that comes from the normalizing factor in the transform. So I have to divide by 2 pi, but I got a factor of 2, right? And now it is, well, I could write the convolution 2 different ways, right? I picked this one. And then here is the one that I'm shifting. So, and of course, this is the integral map of the data to the solution, right? And the way to think of it is, you know, you are at a given point x and y. You want to know what the solution to this problem is for the given data, and you just figure out how the data affects the solution, right? Right. And so this is the Green's function representation. And it's actually got some nice properties. If you look at this weight, so this is the integrand is a positive function. And if you, again, you can do contour integration or Wolfram alpha, look it up in tables, and you get that this integral is 1 for every y, positive y, right? And so this thing here is really showing that the solution is a weighted average of the boundary conditions, right? And just like the Green's, this is just like the Green's function for the heat equation, but of course the shape of the weighted average is different for the two problems. And just like the heat equation, the fact that you are taking a weighted average with positive weights of the initial conditions means that the solution has a maximum principle, right? You can't ever have u of x and y bigger than the maximum value of the initial conditions. So leads to a maximum principle. Okay. we've got an end of Fourier transforms for a while anyway. We've had a problem on the back burner for a while now, right? Let's go back to the simplest sort of PDE that we have, which is the heat equation. So we can have interior forcing, we can have initial conditions, and we know how to handle those, and we know how to handle them separated, right? We can set f equal to 0 and solve the initial value problem, and then we can set, oh, now I forgot what I said first. We can set u0 equal to 0 and solve with the interior forcing, and we can add them up, right? The beauty of a linear problem. We also knew, right, that there were other, I picked B for boundary condition, right, boundary values. We also knew that we could separate out the problems for B0 and B1, right, in the same way, then have all the other stuff 0 and just consider those problems on their own. But maybe you've lost track, but we have not worked out how to handle those terms yet. So again, we can divide and conquer. So let's focus on the problem that's just got these boundary conditions. Right, this is just one of 4 problems you would solve and paste them together, right? So let's look at this guy. And in an assignment question, I think it was on the last midterm, students reminded me of one way to do this, right? Which is there's a trick, right? You can turn the boundary data into interior forcing. So I'll say 1 path forward. We can turn boundary data into interior forcing. And enough students did that. I think they talked about some lectures in Math 257 with Anthony Pierce, and this is an idea that you had from them, right? So that is, let's zero out those boundary conditions and move the influence of the boundary conditions into some interior term, right? And here is the typical way you would do that for this problem. Is you look at a problem where you subtract off the boundary conditions. Okay. So this is the obvious choice in this problem, right? For the term as a function of x, but you could use any function of x with f of 0 equals 1 and f of 1 equals 0. Now, the beauty of this one is that there's going to be a second derivative of this thing that you added that gets put into the interior forcing term. And if you take the second derivative with x of the particular one that's the natural one to take, then that term is not present, right? So this is a nice choice in this particular problem, but otherwise it's arbitrary. So now if I look at the equation that V satisfies, right? I've just added some stuff, so I know it's going to satisfy the heat equation with a right-hand side forcing term. Let's look at what that is. Well, that's ut minus uxx. And now I've got to subtract the time derivative of this minus the second space derivative of this. But like I said, that term is not zero. So now I just get the time derivative of this quantity, right? And so now, right, I can solve for V and then get u from this relationship. And V solves a nice problem. Right, so, right, this is the thing we know how to solve, right? We could even combine the things together if we went back to this original problem. Where did it go? This one, we could add in these terms to the ones that show up here, right? And in fact, that would be the right way to do it, right? So yes, we did have some time-dependent boundary conditions, but we've just done some tricks to put them in the form of forcing terms elsewhere. So this is a way to go, right? And it's a way to go that you can make, you know, theoretical progress with and analytic progress with if you've got particular problems you want to solve. But I want to show you an alternative, which is going to be sort of a cleaner way to look at these kind of boundary value problems, okay, and more general. So, so as an alternative, we can solve the pure boundary value problem. That's this one. With the Laplace transform. Okay. When I was an undergraduate, the Laplace transform was not my friend. Okay. The Fourier transform became my friend eventually, but certainly not that. Now, I could be projecting, okay, but maybe the Laplace transform is not your friend either. And so let's go back and let's look at the Laplace transform in review. Okay, so I can take the Laplace transform of a function f of t defined for t bigger than or equal to 0. So just like this function b0, this boundary value term, I'm going to be able to take its Laplace transform. Okay, and what is it? Well, I had hats for Fourier transforms and transform variable alpha. I'm going to have tildes for Laplace transforms and use S, which I think is typical for Laplace transform variables. So I'm going to have f tilde of S. So I started with the function of t. I get f tilde of S. And this is the formula. Right. So I can say this is, I take a function for defined for t greater than or equal to 0. And I get this function of S coming out. And the way to think of it is, which will come up later, think of S as a complex variable. I've said this before on other sort of review material I've done. Of course, I apologize to all of the students for whom the Laplace transform is their dear friend, right? And they don't need this review. But I'm almost sure that's not true of everyone in the class, and so this is for the rest of the students. Okay, so if I have at least some exponential bound on how big this function can be, right? So, right, there are lots of problems where we want to look at where there's exponential growth in time. And all I'm saying is that's as most as it can be, right? It can be some fixed exponential growth, but no more than that. So this is for all t with some fixed positive constant. Then I can define this thing. This thing is going to be defined for all complex S with the real part of S being bigger than alpha, right? Because then whatever exponential growth I have multiplied by something that has even bigger exponential decay, and you can always integrate out to infinity something that's decaying exponentially. Okay, so now we're getting sort of foreshadowing the sort of theoretical stuff, which is what I was hazy on as an undergraduate student. So this defines f tilde of S actually as a complex analytic function for real S bigger than alpha. And so then I can do the complex continuation to other values of S. Okay, and of course there will be possible singularities, poles, and branch lines. Okay, so Math400 stuff. Okay, so there are some examples. This is the thing I never liked about the Laplace transform was in all the things that got used for, like it was no different than the method of undetermined coefficients and linear constant coefficient ODEs. So I thought, why do it? Well, okay, so there is a reason to do it. We'll see some examples where it's quite useful. So this is the back and forth, right? You can do these examples on your own, except maybe the last one. Right, so this is something that's got a pole of order n+1 at s equals 0. This is a pole, simple pole at s equals a. You can do exponentials. Could have done this in a complex exponential form. Okay, and here's one which maybe you don't know, right? It's if I've got f of t is the complementary error function. This is okay, so what is this? The complementary error function. You can see how this can come up in statistics. It's basically some version of the probability in the tail of a Gaussian distribution, right? Right, this is, so I've got the tail of a Gaussian distribution with a certain scaling with a factor. What's the factor? Square root of pi. Okay, so if this is the function you start with, we're going to be reading this backwards. We're going to get something that looks like this out of a PDE problem, and then we're going to know that the solution is some kind of error function that's going to come out. Okay, so we have a tiny table of Laplace transforms and the back and forth. So let's look at some properties. Oh, how's my time? I got 10 minutes of the Laplace transform. Okay, here is where they're useful for solving differential equations. You have a very similar property to the diagonalization of space derivatives with the Fourier transform representation. This is an easy one to get by integration by parts. This is S times the Fourier transform of f minus the initial condition. So L is linear and I'll say invertible on a set of functions, which I'll leave somewhat ill-defined. And again, I've got this same thing going on as with the Fourier transform. If I take the Laplace transform of a convolution, I get a product. One too many brackets. There's a typo in the notes here. I forgot to put the tildes on top of those functions. Right, and then of course you can read this backwards. That says if you want to take the Laplace transform inverse of a product, it is a convolution of the functions that whose Laplace transform was the product you were taking. So I haven't told you how to compute this thing in general, and I'll come back to that next time. But if you have these properties and a table of transforms, of course, the table of sort of useful and known Laplace transforms is quite large. We've only got these 4, but it's going to be enough for looking at the examples we're going to look at. So the next thing that we'll go on to is we'll look at some examples. And then we'll look at a PDE example of the heat equation with the boundary condition, right, that we're going to be able to solve with the Laplace transform. Okay, and then we'll look at the boundary conditions, boundary condition problem when it has a harmonic forcing. And some stuff really interesting comes out of that related to the temperature in soil and how it varies with seasonal and day-to-day variations. It's a simple model that gives some insight into how that behaves. But this looks like a good place to stop. I poached some minutes from you before. I'm going to give you five back today. So we'll pick this up next time. Now it's been announced all over the place, but just in case you've missed it, there is a take-home midterm which will be posted tomorrow morning at 9 a.m. and due Thursday morning at 9 a.m. So that will be the 24 hours. That was a vote we had and an in-class discussion. And solutions to the assignment 6 part A questions will be posted before the midterm is posted. So you'll have those to look at if they're helpful. There's a few students that get extra time, and I have your names. I'll make sure that you have extra time for the midterm, the extra 12 hours. Okay, so I will stop recording here, but stay on in case students